Hi everybody, it's Miss McClellan again, here to go over IM2 Notes 2.1.3 with you. Can I reverse it? Converses. What happens if you reverse a true conditional statement? And will it still be true? We have one learning goal. Let's write it in first person. Given a conditional statement, I will be able to write its converse and determine the truth value of both my original statement and converse. Right away, we have problem 223. In a conditional statement, the if portion of the statement is called the hypothesis, and the then portion of the statement is called the conclusion. Now, if you reverse the order of the hypothesis and conclusion, then you have created the converse of the statement. Here's an example. Consider the conditional statement. If angles are vertical, then they are congruent. This statement is true. I know because vertical angles are congruent. It's a theorem I get to use. I think we proved it in notes 1.1.3. Proven in section 1.1.3. Vertical angles are congruent. And what about the converse? Is the converse true? Well, the converse is made by taking the conclusion. They are congruent. This is the conclusion. And switching it with the hypothesis. Here's the hypothesis. Angles are vertical. So I'll write, if angles are congruent, then they are vertical, period. And this is absolutely false. I know because I can make a counter example. Here's one. Check out this angle. I'm calling it congruent to this angle. They're not vertical. Here, angle A is congruent to angle B, and they are not vertical, period. The reason we did that, everybody, was to see that the truth of a converse doesn't have to be the same as the truth of its original statement. 2-24. Every conditional statement has a converse. Let's consider this arrow diagram. Triangles congruent implies all pairs of corresponding sides are congruent. Here I read the arrow as implies. In math, to say that a statement is true means that it has to always be true. That's really important. That means that it has to follow from a definition or a theorem. Is that, is this arrow diagram true? Is this true? And it is true. I know because I have the corresponding parts of congruent triangles are congruent theorem. And that's CPCTC for short. I think we learned that in notes 2.1.2. So last class. Part B. Write the converse of the arrow diagram as an arrow diagram or as a conditional statement. Is the converse true? Let's justify our answer. Okay. The converse is going to switch my hypothesis and my conclusion. So all pairs of corresponding sides are congruent is my original hypothesis. And that's going to become, is my original conclusion, sorry. And that's going to become the hypothesis of my converse. So all pairs of corresponding sides are congruent implies, and the conclusion of my converse should be the hypothesis of my original statement. And so I'm going to say that all pairs of corresponding sides are congruent implies that triangles are congruent. And that is also a true statement. I know because it is the side congruence theorem. Period. So here we have a situation where the original statement is true and the converse is also true. I'm starting to notice that the truth of the converse is independent of the truth of the original statement. One does not depend on the other. Okay, next problem, 2-25. For each statement below, we will rewrite it as a conditional statement or as an arrow diagram and state whether it is true or false. Then we will write the converse of the statement and tell whether it is true or false. Try to remember that for a mathematical statement to be true, it has to always be true. Okay, my original statement is all squares are rhombuses. Let's identify my hypothesis. It's a square. And my conclusion, it's a rhombus. The conditional statement is all squares. Instead of saying all squares, I'll just say is a square. Arrow diagram is a rhombus. And this statement is true, I know, because in order to be a rhombus, you need 4 congruent sides and that's what a square has. And that is what a square has. Now, let's check out the converse. The converse is if it is a rhombus, then it is a square. See, I flipped it. And the converse is not true. The converse is false. I know because a square needs 4 right angles, which a rhombus does not guarantee. Now, students, I'm going to suggest, if you're hearing all of this stuff and you're like, what? How am I supposed to know that? Please see your notes 1.1.2 to remind yourself about polygons. That was your polygon page. Okay, part B. Original statement. Every isosceles triangle is equilateral. The conditions. Well, I've got isosceles. That's going to be my hypothesis. So is equilateral is going to be my conclusion. And isosceles is my hypothesis. The conditional statement is if it is an isosceles triangle, then it is equilateral. And this statement is definitely false. I know because I can come up with a counterexample. And anytime you're saying one of these statements is false, you really should be providing me with a counterexample. Here's one. Consider this triangle. I'll say that it has 20 degrees here and 20 degrees here. Well, this is isosceles. And it is not equilateral. Because an equilateral triangle needs to have all 60-degree angles. Let's write the converse. The converse says if a triangle is equilateral, then it is isosceles. And this one is true. All you need to be isosceles is to have 2 sides of equal length, and your base angles need to be congruent. All equilaterals satisfy the requirement for isosceles. And that is at least 2 pairs of congruent sides and angles. Okay, part C. The original statement is that two pair lines cut by a transversal from. So my hypothesis is that I have 2 parallel lines and they're cut by a transversal. form same side interior angles that are supplementary, and that's my conclusion. So the conditional statement is parallel lines cut by a transversal implies same side interior angles are congruent. And this conditional statement is indeed true. I know, because it's one of my theorems. This is the same side interior angles theorem. As a visual reminder, it is this one. Let's write the converse. We have to switch the hypothesis and conclusion. So for the converse, we start with same side interior angles are congruent. And we write that implies parallel lines are cut by a transversal. In particular, it implies that the lines that are cut by a transversal are parallel. So I'm going to rewrite that to be more clear. The lines cut by the transversal are parallel, period. And this happens to also be true. And in order to prove it, we can use corresponding angles. So I'll do a quick kind of hand-wavy argument proof. Let's let this be A, this be C, and this be C. Angle A is congruent to angle C by corresponding angles. Or just suppose, because I should start with this fact. Suppose angle A. I'm sorry, everybody. I've got this. I know exactly what to say now. Suppose angle A plus angle B equals 180 degrees. From the diagram, angle B plus angle C also equals 180 degrees. That implies that angle A is congruent to angle C, which means the lines are going in the same direction and therefore are parallel, period. Okay. Yay, last page. We're going to summarize our learning from the day. We have conditional and converse statements. Here's our word bank: hypothesis, conclusion, converse, conditional statement, and arrow diagrams. Conditional statements, or if-then statements, basically a conditional statement is like a promise with a condition. If you finish your homework, then you can play video games. If you finish your homework, that's the condition, then you can play video games. That's the promise. They can also be written as arrow diagrams. In math, the if part, if you finish your homework, is called the hypothesis. So the condition is the hypothesis. And the then part is called the conclusion. Now, the converse of the conditional statement. The converse of a conditional statement is what you get when you take the original statement, do a little flip, and reverse it. If you switch the original hypothesis and conclusion, then you might not get the same truth value. For the converse of our homework and video games example, playing video games is now the hypothesis and finishing homework is now the conclusion. So we've switched them. Becoming, if you're playing video games, then you finished your homework. But it is crucial to note that while it may seem logical to assume that if a conditional statement is true, its converse must be true, that is not always the case. Just because you're playing video games doesn't mean you finished your homework. Maybe you're just really good at sneaking in game time. The original promise does not always apply in reverse. That's the end of these notes. I hope you found them useful, and I'll see you next time. Bye. Thanks for watching.